In the last video, we talked about the transformer, the voltage, current, and the impedance relations between its primary and secondary sides. In the end, we derived the equivalent circuit of the practical transformer with a number of non-idealities accounted for. Now let's think about how an induction machine works. So if we connect the stator to a three-phase AC power source, current in the stator winding will create a rotating magnetic field due to Ampere's law. This process is actually identical to the process that happens on the primary side of the transformer. So you can think of the stator of the induction machine as the primary side of the transformer. In the induction machine, the magnetic field then goes across the air gap between the stator and the rotor. Right here, there's a small air gap here. Right, that's the separation between the rotor and the stator. That magnetic field crosses the air gap and then cuts the rotor bars, and then induces a voltage and a current in the rotor. In the transformer, the induced magnetic field crosses the transformer core, and then induces voltages and currents on the secondary side of the windings. So the rotor in the induction machine is just like the secondary side of the transformer. So in fact, the essence of operation inside the induction machine is actually identical to that, to the fundamentals inside the transformer, except that the rotor inside the induction machine has a mechanical rotation, but there is no mechanical rotation in a transformer. So this is the equivalent circuit for the practical transformer we derived in the last video, and to adapt it to the induction machine, we have removed the load ZL. In the end of the previous video, we have a load ZL here, right? But here we have removed that load because the rotor in the induction machine is usually short-circuited, so there's no explicit load that's attached to it. So here we have removed that. And aside from this very minor change, the equivalent circuit of the induction machine is actually identical to that of the practical transformer. The reactances X1 and X2 that account for the stator and the rotor side magnetic flux leakages might be higher than those in the transformer because there is an air gap, right? Because there's an air gap between the stator and the rotor. But in the transformer, it is actually the transformer core that links the primary and secondary windings. So in the induction machine, the leakage could be larger, right? The flux leakage could be larger. So X1 and X2 could be larger in the induction machine than in the transformer. And there is another effect of the air gap, right, which is the so-called reluctance of the magnetic flux path. Right, the air gap actually increases the reluctance of the magnetic flux path. The reluctance is a concept that's kind of similar to resistance. Right? So if the reluctance is higher, we will need to spend higher magnetizing current to induce the same level of magnetic flux. Right? So reflected on the equivalent circuit, it means that the magnetizing reactance X0 is smaller in the induction machine than in the transformer. Aside from these differences, there's really no difference between the induction machine and a practical transformer. But another point that we need to pay attention to is that for the induction machine, there are three phases, right? Usually we have three phases. It's a three-phase induction machine. So the equivalent circuit that we're actually looking at right now, and it has a turns ratio of 8:1, right? It's actually per phase. So this diagram is per phase, right? So for the three different phases, we have three copies of the same diagram, right? So this turns ratio is actually per phase also, right? So if you have windings or coils on the rotor, those wounded rotor, right? Then this A actually accounts for the turns ratio per phase, right? And if we have like 3 phases, then we have to sort of duplicate the same diagram like 3 times. For squirrel cage rotor, this turns ratio A has to be sort of converted to some sort of equivalent value, right? Because on the squirrel cage you don't really have coils; it's not windings, right? So you have to sort of convert the squirrel cage windings into some sort of equivalent turns ratio, right? So that's sort of slightly more complicated, right? But in this case, we don't worry. But in our study, we don't worry about that. So when we try to actually compute the mechanical power and the torque later on, we need to remember that this kind of diagram is per phase, right? And we need to actually multiply a constant factor of 3 to account for the fact that we have 3 phases, right? All the results derived by looking at just this diagram gives us the result for just one phase. So we need to multiply 3 to account for 3 phases. Back in video 17, we derived these 2 very important equations for the frequency and the voltage induced in the rotor. So the frequency in the rotor, it's AC current or AC voltage is in the rotor, right? So for those AC signals, they have frequencies, right? It's not a direct current. Direct current has a frequency of 0, right? But for those AC current, you have non-zero frequencies, right? So FR is the frequency of the voltage and the current inside the rotor. So FR. And FR equals to S is the slip, which is just the speed difference, the rotational speed difference between the rotating magnetic field and the mechanically rotating rotor. That's divided by, normalized by the synchronous speed, which is the rotating speed of the magnetic field. So that's the slip. So slip times the frequency in the stator, Fs, right? So there's a frequency difference inside the rotor and between the frequency inside the rotor and the frequency inside the stator, right? It's different. It's different frequency once you have a slip, right? And then the induced voltage, capital ER, actually equals to the slip times the so-called open circuit voltage, E. Here it's capital E, it's not a small e, right? In previous videos, we have been using small e, right? Small e to represent voltage. Those are instantaneous values of voltage, but here we are using effective values. The exact difference between those effective values and instantaneous values, we haven't actually spent some time to discuss that yet. If we have time, we can actually talk about those differences, right? But here we're actually using effective values. It's kind of a sort of an average of instantaneous values over a certain period of time, basically. But you can think of it just as some kind of average, right? So we will be using these 2 equations when simplifying the equivalent circuit of the induction machine, right? We will start by examining the equivalent circuit of the induction machine under the standstill condition. That is, when the rotor is not rotating, right? If it's not rotating, then the slip, which is the speed difference normalized by the synchronous speed. So if the rotor is not rotating under the standstill condition, the rotor speed is 0, right? The rotor speed is 0, then the speed difference equals to the synchronous speed, right? So the slip is the speed difference divided by synchronous speed. So the slip becomes 1, right? So under the standstill condition, the rotor frequency Fr is actually identical to the stator frequency Fs because S equals to 1, right? And then the rotor voltage Er, the induced voltage inside the rotor, is identical to the open circuit voltage. Right. So let's start from that. Let's start from the standstill condition. So if we look at the equivalent circuit of the induction machine, the voltages and the frequencies in the stator and the rotor can be obtained, right? Can be obtained. So if the voltage on the stator side is E1, right? We're looking at the voltage across these 2 ports, basically, right? So the voltage here could be quite different, right? But let's suppose the voltage here is E1, right? That's the E1. That's the voltage. That's going to induce another voltage across this ideal transformer with a turns ratio of 8 to 1. Right? If the voltage on the stator side is E1 and the voltage on the rotor side E2 should be equal to the so-called open circuit voltage, right? This is standstill condition. So EOC is the open circuit voltage, and the open circuit voltage under this kind of condition is what is if you consider the turns ratio 8 to 1, then it's E1 divided by A, right? So on the standstill condition, E2 equals to E1 divided by A, and the frequency in the stator is F1, suppose, right, which is equal to Fs in the previous slide. So here we're using Fs here, but here let's just change it to F1, right? And then the induced frequency in the rotor is F2, right? Let's call it F2. Let's call it F2. And on the standstill condition, because the slip is 1, so F2 equals to F1. That's Fr equals to Fs, right? That's exactly the same kind of relation, because F1 equals to Fs. F2 equals to Fr, right? So F2 equals to F1. So now, what will happen if we allow the rotor to rotate, right? If the rotor starts rotating, then the slip is not unity anymore, right? It's not a 1 anymore. So, so what's going to be the difference, right? So E2 will not be equal to just the E1 divided by A anymore. E1 divided by A only accounts for this turns ratio, right? But you also have to account for the fact that the rotor is rotating, right? So if the rotor is rotating, E2 actually equals to S times EOC, the open circuit voltage, right? So it becomes S times E1 divided by A, right? So if you have a rotation, then E2 is going to have a factor S multiplied into it, right? That's one of the differences. And then there's another difference, which is the frequency, right? So F2 is not going to be equal to F1 anymore. It's going to equal to slip S times F1, right? And this problem is kind of more difficult to deal with, because the transformer only accounts for the differences in the amplitudes of the voltage and the currents, right? It does not account for differences in the frequencies of the voltages and the currents. So how do we actually account for the frequency differences, right? Once it starts rotating, frequency will be different. So how do we actually account for that? By using the transformer circuits, right? We try to replace the rotor side circuit with an equivalent circuit that has the same frequency as the stator side. So if we only examine the rotor side circuit, right? We have so now the E2 equals to slip times E1 divided by A now, right? So that's sort of the amplitude difference, and that's sort of the amplitude under the rotational speed of given for slip given by S, right? If we look at this particular circuit, we have only like 2 passive components, right? R2, this resistor R2 accounts for rotor side copper loss, basically, and the inductor with the reactance of X2 accounts for the rotor side magnetic flux leakage, right? So only the inductor's reactance actually depends upon the frequency. So if we can write the reactance on the rotor side as the angular frequency omega 2 times the inductance L2, right? And then this is the angular frequency, right? If we convert it to hertz, then that's F2 times 2 pi, right? That's the angular frequency, and then it's 2 pi F2 times multiplying L2, the inductance, right? And we know that F2 actually equals to the slip times F1. F1 is the stator side frequency, right? So X2 actually equals to 2 pi slip times stator side frequency times the inductance L2, right? And this term actually depends upon the slip, and the slip times F1 equals to F2, right? So this is so S times F1 is different from F1, right? That's the F1 is the stator side frequency, but S times F1 is kind of different from the stator side frequency. So our goal is to just to replace this inductor at frequency S times F1 with another equivalent inductor with a reactance that's given at frequency F1. So we want to get rid of the S here. Without disturbing other things in the circuit, right? So how can we do that, right? So how can we do that? So one necessary condition that we have to follow is that we don't want to change the current. Right? We don't want to change the current during our conversion. So the current flowing through the circuit before and after the conversion must be sort of identical to each other, right? So how do we actually represent the current here? So on this left side, I2 equals to what? I2 equals to E2 divided by these two impedances sort of connected in series, right? So it's just an addition. So R2 plus J times X2, right? And we know that E2 equals to what? E2 equals to the slip times E1 divided by turns ratio A. So SE1 divided by A. That's E2, right? And then R2 plus JX2, right? So suppose X2 can be replaced with something else. That's S, the slip, times X2 wiggle, right? Suppose we can replace the reactance X2 with slip S multiplying another reactance, a different reactance, that's X2 wiggle. So X2 wiggle has a value of what? X2 wiggle has a value of X2 divided by S, right? So suppose we have an inductor with this X2 wiggle reactance, then we can replace X2 with just the slip times X2 wiggle, right? And once we have done this kind of replacement, we can actually cancel out the slip S from both the numerator and the denominator. So if we do that, the numerator becomes E1 divided by A, right? And then the denominator becomes R2 divided by S plus J times X2 wiggle, right? So E1 divided by A is what? E1 divided by A is the open circuit voltage, right? That's open circuit voltage. We have accounted for the turns ratio now, but now we have actually removed the effect of the rotation caused by slip, right? So the voltage here doesn't have a slip term in it anymore, and that's EOC basically, right? That's the open circuit voltage. And then the denominator has two terms, right? The denominator has two terms. A resistance R2 divided by S, and then a reactance given by X2 wiggle, right? So this part is relatively easy because all we have to do is to replace R2, this resistor, with a different resistor, right? Here we are replacing R2 with R2 divided by S, just to replace the resistor with a different resistor. Then the other term, JX2 wiggle, means that we have to replace this inductor with a different inductor with the reactance given by X2 wiggle now, right? So X2 wiggle, what's the expression for X2 wiggle, right? X2 wiggle equals to X2 divided by S, right? X2 equals to what? X2 equals to the angular frequency omega 2 times the inductance L2, right? Again, if we convert the radian angular speed to hertz, radian angular frequency to hertz, F2, right? Then 2 pi F2 times L2, right? F2 equal to S times F1, right? S times F1, that's F2, right? And then don't forget that we're dividing S here. We're dividing S here, so this S and this S cancels out, right? So X2 wiggle equals to 2 pi F1 times L2. Here we have F1 now, right? That's the frequency of the stator side frequency. That's F1 is the stator side frequency, right? So the inductance L2 is the same, right? But the frequency has been converted to the stator side frequency. It's no longer F2, right? It's not F2 anymore. It's actually F1. Right? And then this term doesn't really have slip in it, right? So this is just the frequency of the stator side. It's a stator side frequency, F1. Right? So if we do these two replacements, replace R2 with R2 divided by S, and then replace X2 with X2 wiggle, then this equivalent circuit operates under F1, the stator side frequency, F1, right? So by doing this kind of conversion, we have actually accounted for the frequency difference between the stator side circuit and the rotor side circuit. And this equivalent circuit, this thing, with R2 divided by S as the resistor and X2 wiggle as the inductor, can now be integrated into the stator side, basically, right? In the previous video, video 21, we talked about how to map secondary impedance on the secondary side, basically, to the primary side, right? And the equation we obtained was that the apparent impedance on the primary side actually equals to the turns ratio squared, multiplying the secondary side impedance, basically, right? And that's the equation that we're going to use to actually map the rotor side of the impedances to the apparent impedances on the stator side, right? So the same is true here for the induction machine. So the stator side apparent resistance for the resistor R2 divided by S is just the A squared, the turns ratio A squared times R2 divided by S, right? And the same is true for the inductor, right? All we have to do is to multiply A squared, the turns ratio squared, and then that's the apparent impedances for the stator side. And then once we have moved those components to the stator side, the transformer is useless now. So we have actually removed the transformer from this side. There's no transformer. You don't see the transformer anymore, right? So in the literature, a common practice is actually to represent the apparent impedances that account for the effects of turns ratios with a prime, right? So here we have actually sort of converted the A squared times R prime times R2 with R2 prime, right? So R2 prime basically accounts for the effect of the turns ratios, right? And then here we have replaced X2 wiggle times A squared with X2 wiggle prime. So that's sort of a convention that's kind of used quite widely in the literature, right? And then here we have the current that flows through this kind of a stator side, rotor side circuit is represented as I2 prime, right? So if this is all those currents I1, I2 prime can be actually solved if we are given a kind of a input voltage, right? All those things can be actually solved because you have a circuit here. It can be solved using KVL, KCL, those relations, and they can be solved, right? But let's not worry about what the solution actually is. Let's just sort of take a look at what the circuit actually tells us, right? So if the current that flows through the rotor side of the equivalent circuit is I2 prime, right, then what's going to be the power that's dissipated on this particular resistor, right? That's an that's something that's called an active power. We haven't actually talked about the differences between active power and reactive power yet, but you can sort of imagine that if there's a current I2 prime that flows through this resistor, there must be some power dissipated by this resistor, right? And that power equals to what? Right? Power equals to voltage times current. Right? Ohm's law tells us that for a resistor, voltage equals to what? Voltage across the resistor equals to the current multiplying the resistance, right? So the voltage actually equals to the I2 prime multiplying R2 prime divided by S. That's the voltage, right? And then what's going to be the current, right? The current is just the voltage multiplying the current, the power, or the power is just the voltage times the current. So the power is I2 prime squared times R2 prime divided by S, right? So that's sort of the power, the active power, that's actually flowing through the air gap from the stator, from the stator to the rotor. Right? So the power that's dissipated by this particular resistor is the active power that goes across the air gap from the stator to the rotor. Right? So we know that the R2 prime is the apparent resistance of the rotor side winding appeared on the stator side, right? But what exactly is the resistance that's R2 prime divided by S, right? What exactly is this term? What exactly is this resistor, right? So to understand that, let's try to split this particular resistor into two terms, right? So R2 prime divided by S equals to what? Equals to R2 prime plus R2 prime multiplying this slip dependent term, right? So basically we can split this particular resistor into two different resistors. One is just R2 prime, and then the other resistor is this kind of R2 prime multiplying this slip dependent term. That's another resistor, right? So if you add these two resistors up, you get this resistor back, right? So let's split that resistor into these two different resistors, right? So the copper loss, the energy dissipated by the rotor side winding is I2 prime squared times R2 prime. So that's the copper loss, right? That's the copper loss. And then what about the energy that's dissipated on this sort of a fictitious resistor, right? It's not a real resistor. This is the real resistor. That's the resistance on the copper wires, on the wiring of the secondary. But this one is a fictitious resistor, right? It's not really represented by any kind of electric component on the rotor side, right? It's a fictitious resistor. So what about the energy that's kind of dissipated by this fictitious resistor, right? The power dissipated by this fictitious resistor is actually the electrical equivalent of the mechanical power on the rotor. The rotor is rotating, right? The rotor is rotating. Rotating means that it has a rotational speed. The rotational speed goes into the slip S. This thing doesn't have a speed in it, but this thing has a mechanical speed in it. Right? This resistor has a mechanical speed in it. Right? So the electrical power that's dissipated by this fictitious resistor is actually connected with the mechanical power. Right? So if the induction machine is working as a motor, then the energy dissipated by this fictitious resistor is converted to mechanical power. That's going to drive a load. And if it's actually working as a generator, right? If it's working as a generator, S is a negative number, right? We talked about that in a previous video, right? And then the power dissipated by this fictitious resistor actually becomes negative. A negative power means what? Means it's not energy dissipated. It's actually energy generated, right? So in any case, the power on this fictitious resistor is related to mechanical power, right? It's either generated mechanical power or dissipated mechanical or used mechanical power, right? So this is actually indeed a remarkable result. It's indeed a remarkable result. Right? And now we have an electrical representation of the mechanical power in our equivalent circuit, and that power equals to what? Equals to I2 prime squared multiplying this particular resistance. That's R2 prime times this slip dependent term. Right? That's sort of the electrical equivalent of the mechanical power that goes into or out of this mechanical system. Right? We have, by just looking at this fictitious resistor, we actually have coupled the electrical domain to the mechanical domain. Right? It's indeed a very, very powerful result, and it looks so clean. It looks so elegant. Right? It's a very elegant result. So the mechanical power equals to what? Right? The mechanical power equals to what? So here we still have no idea what the I2 prime actually is, right? But later on we'll worry about that later on, right? What I'm saying is that I2 prime can be solved. It can be solved. We haven't actually solved it, but the solution can be found, right? What exactly is R2 prime, right? And all those things can be figured out, right? And we don't have to figure them out because other people have solved the problem for us, right? And later on we're going to look at other people's solutions, right? But now let's try to understand. Once we have this representation of the mechanical power, how do we actually get the torque, right? How do we get the torque? The torque equals to what? The torque equals to the mechanical power divided by the angular speed of rotation, right? So what's the angular speed of the rotor, right? So suppose the angular speed of the rotor is capital omega r. In previous videos, we were using small omega r, right? But small omega, I was using small omega in this video to represent the angular frequency, right? I was using small omega to represent angular frequency here, right? So here let's change it to capital omega. Capital omega r is the angular rotational speed of the rotor, right? And then the slip equals to what? Slip equals to the synchronous speed of the rotating magnetic field inside the stator, subtract the angular speed of the rotor, and then normalized by the synchronous speed, right? Omega s, capital omega s here, right? And then we can simplify it into 1 subtract omega r divided by omega s, right? So omega r equals to what? Omega r equals to 1 subtract s, and then multiply omega s, the synchronous speed, right? So here we have an expression for the angular speed of the rotor, which is expressed using the synchronous speed capital omega s and the slip s, right? And then we have an expression for the mechanical power that's given here, right? But don't forget, this is the per phase. This is the mechanical power for just the one phase of the input power source, right? We have three phases. So the total amount of mechanical power is actually 3 multiplying this thing, right? So that's 3 multiplying the whole thing here, and then divided by omega r. That's the angular speed of the rotor. That gives us the torque. Right? That's the torque. So omega r has this particular expression in it, right? So we can replace omega r with omega s multiplying 1 subtract slip, right? And 1 subtract s can cancel out on numerator and the denominator, right? So what have we obtained is 3 multiplying I2 prime squared multiplying R2 prime divided by S and then divided by the standard side, the synchronous speed of the magnetic field, basically. Right. So that's the expression for the torque. So this term that's inside of this red box is what? Is actually the active power that goes across the air gap from the stator to the rotor. Right. And then we divide this power, of course, multiplied by 3 because it's 3 phase, right? And then we divide it by the synchronous speed. Right. The synchronous speed, that's the rotational angular speed of the rotating magnetic field. That's omega s. And this division gives us the torque. Right. And then if we look at this particular thing in the red box, that's the energy dissipated by the fictitious resistor. Right. And then it's dividing by omega r, the rotating, the angular speed of the rotor. And then this division also gives us the same torque, right? So do you see the kind of a consistency in these two representations, right? This is the power dissipated by the fictitious resistor. And then you divide by omega r, the rotational speed of the rotor. Here it's actually the total amount of active power that goes across the air gap, right? And then you divide by the synchronous speed of the magnetic field. You also get the same torque. Right? In the next video, we're going to look at what the torque actually looks like as a function of the slip, right? And we'll discover more interesting results.